So my name is Stephen Parkinson. I am the outgoing White Hat sysadmin, incoming vice president. And I'm going to be talking to you tonight about machswap, which is a vulnerability in the XNU kernel. So brief overview of the talk. We're going to talk a little bit about XNU and Mock, the Mock interface generator, use Afterfree, the vulnerability itself, some garbage collection, parentheses. And then we need to be able to read kernel memory and then read and write kernel memory, which is the TFP0 at the end. So last quarter, I did a talk about jailbreaking. I kind of hand-waved over the exploit the bug to gain the kernel read and write. That is what we are going into tonight. It's going to be a lot of MIG and Mock. Anyway, let's start with XNU. So XNU is the kernel for all of Apple's operating systems. It started with Mac OS, and then iOS was introduced in 2007. tvOS, watchOS, and then the most recent one, Audio OS, which is what the HomePod runs, because they needed a separate operating system for that. It's built on what is called a hybrid kernel. It's not really a thing, but it's basically a monolithic kernel with some processes in user space, which is similar to a microkernel. However, it has no performance overhead when passing between kernel and user. Very little. And so the three components of XNU are Mock, BSD, and IOKit. The one we care about is Mock. And XNU runs on ARM because obviously iPhones and the HomePod and tvOS, TVs. Oh, and the watch. The watch also is ARM. And then x86-64 because Macs are still a thing. So then, yes, what is Mock? Well, basically, Mock is a inter-process communication layer, or IPC layer. It allows processes to talk to one another, including the kernel to different processes. It also is responsible for handling tasks such as what are called Mock servers. Basically, something like the Bluetooth daemon will run on Mock so that devices can talk directly to it and connect to your different devices. It also uses a Mailbox system, which we'll go into now. The Mailbox system is essentially you have messages and ports. The messages you can consider letters. The ports you can consider the mailboxes. So different ports will have different writes. So there's a send write and a receive write. So if a port only has a receive write, obviously it can only receive messages. If it only has a send write, it can only send. And then if it has both, it can do both. And then ports have addresses in the XNU kernel, which are called handles. That'll be important in a little bit. Yes?
Wait, so processes can write to ports. What's the connection between ports and processes?
So the Mock ports themselves are basically just something that a process will have access to so that it can talk to another process.
So the process has access to the Mock.
So
like,
yeah,
there's a Mock port for writing to Mailbox A.
Yes, yeah. Mock has its own API calls and stuff like that, so that the processes will have access to the ports that it is keeping track of. So now we go into MIG. MIG is the Mock interface generator. Because writing Mock code is very tedious and people didn't want to do it, Apple created the Mock interface generator. Basically, it is a service that will generate definitions for functions for you. And it handles all of the communication within Mock for the processes. And then this is an example of some MIG code. This will create a JBD underscore call function accessible from the Mock API. This is part of the Jailbreak D system daemon that was part of the Meridian and Electra jailbreaks. Yeah, so essentially MIG is designed to generate code that makes our lives easier. Side note, it also tracks reference counts to things, which we might care about. And then last little bit of background, the use Afterfree. Essentially, use Afterfree allows, or it's basically someone using an object after it has been dereferenced. So if you have some object that has a ref count, if you're able to decrement that ref count somehow from a different process and another thread is keeping track of it, then the thread that's keeping track of the thing that you have now gotten rid of will still have access to it. And then if it's released to the allocator, if its references go down to 0, it will be cleared out, and basically you have a pointer to some memory somewhere that you shouldn't have. So what is the vuln? Well, it is from some MIG code generated around the task swap mock voucher function. Task swap mock voucher itself, fairly simple. As you can see, it takes 3 arguments, task new voucher and in-out old voucher. And then if the task is a valid task, it will set the value of in-out old voucher to the new voucher, and then return success. Perfect, right? Yeah, it does exactly what we want. It does. However, the MIG code generated around it is a little more complicated. And this becomes a problem because the MIG code actually has no understanding of what the kernel is doing. So MIG doesn't know what happens in task swap mock voucher. This is a problem. Also, do you see why we don't want to write this? It's like annoying, probably. I don't know. I've never tried to write mock. Yeah, so basically in this chunk of code, we see that the vouchers are incremented by 1, or the ref counts are incremented by 1. There's those 2 green arrows, and then decremented by 1 at the red arrows. So let's walk through what's actually going on here. We increment new voucher. We increment old voucher. Then we run task swap mock voucher. And if you remember, that sets old voucher to new voucher, right? So then we decrement new voucher, just as we should, obviously. We don't need more references to it because we are done with the task. Then we do it again because we are decrementing old voucher, which is now new voucher. So this code does not decrement new voucher and old voucher. It decrements new voucher twice and old voucher 0 times. So old voucher is gaining references. New voucher is losing references. Yeah.
Why do we not get a new reference to new voucher? Oh, because we're doing just... Are those... Is this C?
I believe it is C++ or C. I'm not sure.
Because like if we're doing some... Okay.
Yeah, I'm not sure. Yeah, so effectively you're decrementing new voucher twice, and old voucher is just gaining a reference. So the struct of a voucher. We don't really care about most of this. The things we care about are the IV refs and the IV ports. The port will be important later for the actual gaining of TFP 0. So now that we have some pointer to some area of memory, we need to trigger garbage collection. To do that, you can do some stuff with a kext called IO surface. It's a bit too in-depth for this talk, and it would take a long time to explain, so we're just going to hand wave over that. We triggered garbage collection. Yay. So now we can use this FakePort, which we have created. Basically, we control what FakePort is. Because we are the ones who allocated and control FakePort, this is just a fake voucher struct, basically containing a bunch of refs and a fake port that we control. This is what we are going to spray onto the heap so that we can get our pointer overlapping with the new ports that have been allocated. So what we have accomplished here is essentially filling the heap with attacker-controlled data, those voucher structs, which contain the fake port that we control. If this is done successfully, we have a pointer pointing to an arbitrary voucher struct. So essentially, the heap spray is getting the IPC vouchers to overlap with the pointer, which will let us get a user land handle on an IPC port theoretically owned and managed by the kernel. So how do we get the voucher into userland? Do you have?
No, I'm
No?
curious how we get the voucher into userland.
Cool. So the port we have stashed on the thread, the pointer to the voucher, is the fake IPC voucher. The fake IPC voucher points to a fake IPC port, which is part of the fake port that we generated earlier. The fake IPC port is allocated in user space as fake port. However, the voucher itself is in kernel memory. So fake port is in user space. The voucher is in the kernel. So we need a handle on the voucher. That's fairly simple. We just use a function called ThreadGet Mock Voucher, which takes our fake port and returns the voucher that it relates to. So now we need to build a read primitive so that we can read the kernel memory. Yeah.
I'm sorry, I got lost on the last one. So
That's fine. Yeah.
we have the voucher. The IPC voucher is in, what is in kernel memory?
So in kernel memory, basically we just have a bunch of, because we sprayed the heap with a bunch of our fake voucher structs. So what we have a pointer to is essentially somewhere where there used to be a port or a voucher that was controlled by the thread. It got replaced by the ports that are controlled and managed by the kernel. However, because when we created it, we put our fake port in it, we have control over the fake port part of it, which is the important part.
Okay, so we've sprayed the heap with these fake ports.
Yes.
And now because it's allocated as free, we have the chance to basically have there is a handle to a voucher, but that voucher is part of that voucher is overwritten by the fake ported portion.
Yes.
Because of the heap spray.
Yeah.
Okay, but that's all in kernel.
Yes.
Okay. And then I'm very confused how. Oh, and then the ThreadGet will copy that into user space?
So yeah, ThreadGet will basically just take the fake port, which is within the voucher, which is in kernel memory.
Okay.
So the ThreadGet mock voucher will take that port and return voucher that it relates to, because a voucher struct has the port number, or the port that it relates to.
Oh, so we're taking our fake voucher struct.
Yeah.
And copying that from kernel memory to user memory.
I believe so, yes. Yeah.
Okay, we're taking that, copying it from... Okay. I think I got it.
Okay.
I'm gonna keep watching.
Yeah. Okay, so now we need to build a read primitive so that we can read from the kernel memory. So we use the function called PidForTask. It returns the process ID of a process of which you provide a task port for, which is the same port that we have earlier. And because we have control over FakePort, we can change what data it points to. So the PidForTask will call the function getBSDTaskInfo, which BSDTaskInfo will return a section of memory at the port that you gave it. So this port can be an arbitrary position in kernel memory. So BSDTaskInfo will return 32 bits of kernel memory at a time if you give it the correct port to look at. And then if you want to read 64 bits, you can just combine two of those calls and then just mush the two together. And then you have read 64 bits of kernel memory. So yeah, basically, we can control FakePort and pass it to getBSDTaskInfo, and it will return some amount of kernel memory. Does that make sense? Yeah? Cool. So we're also going to hand wave over KSLR a little bit. But so in, I believe it was OS 10 at that point, 10.8, Apple introduced ASLR for the kernel, address space address space layout randomization for the kernel. So basically, it will shift around static data to a random memory location from some offset. The space that it has to do this is about 530 megabytes. So just guessing where the data we need is, can't do it because you're bound to run into some memory that hasn't been mapped, and then that would cause a kernel panic, and that's not what we want. So we need to calculate what's called the kernel slide. This is the hand wavy part. We can just assume that we did that, and yeah, it's actually pretty interesting how this is accomplished. And if you want to learn more about it, I would recommend reading the machswap write-up by Ivy Sparkles. Very quality. Yeah, so basically, KSLR, it does this to the memory. So
that's awesome. Oh, that's really good.
Yeah, so it shifts stuff around, hand wavy over it. We now calculated the kernel slide, and we know where all of the kernel structures and stuff like that is located. So now the last part of this is that we need to build a fake kernel task port. Because currently we have a task port in userland, but that's not what we want. We want kernel. So then we can change all the things. So yeah, so what do we need to do that? A kernel task port is just an IPC port of type IKOT task. So we already have an IPC port in FakePort. However, there are two things that you need to make the Mock API actually respect your port as a kernel task port. Yeah.
So just to be sure, a kernel task port is the port was the mailbox, right?
Yes.
So a kernel task port is, if we write here, the kernel will read this message?
Yes, essentially. Yeah, so.
Cool. I'm on board.
Yep. So yeah, we have the two things we need are the kernel's VMmap, are the virtual memory map, so where all of the kernel's code and everything is, or the kernel's virtual address space, basically. And then IP receiver, which is where the kernel stores mock messages that are in transit. So basically, the IP receiver is the receive port for the kernel. So, VMmapT, how do we get that? We can use the BSD info to get the proct of our process, or basically the struct that a process has associated with it. So if we use BSD info to get the proct, conveniently, proct contains a linked list of all of the processes, including kernel task, because kernel task runs as a process. As you can see, there's activity monitor on my laptop, kernel task right up there with screenshot, because I was taking a screenshot. And VMware, yes. Yeah. Anyway, sorry, I was looking at my activity monitor. Anyway, proct task. So we loop backwards through the list until we get to PID 0, process ID 0. So now that we are at the kernel, we can get the task, or the proct task of the kernel, and that contains the task t struct, which contains VMmapT. So doing that, we have the VMmap of the kernel, and we can just assign it in our in the voucher that we have in userland. So to get the IP receiver, so as I said earlier, this is where mock messages are stored when they're in transit. Using the previously created read function that we hand waved over, we can, we hand waved over the 64-bit read part. Basically, it's using two of those 32-bit reads that I mentioned earlier, and the person who created the write-up had created a function to just call this automatically so that it would read 64 bits every time. So yeah, basically we need something that is sending the kernel things for the kernel to do, right? So what might do that? A kernel extension. That's what would do that. So as we used earlier, the IO surface is a good kex to do this. As part of the garbage cleanup earlier, we gained the task T, or the task port of the IO surface client. So we have the task port for a kext. So basically, we use that and read where it is writing messages, because it has to store that somewhere. The text just stores it, and we can read that value, which is 64-bit address, and then get that into our FakeTask port. And yeah, basically, you now have so if you set the FakeTask, which is what we have from earlier, if we set the FakeTask map to the kernel VMmapT and the FakePort IP receiver to the kernel's IP receiver, then the FakePort can now read, write, and allocate kernel memory, all backed by the kernel buffers. So yeah, so how does this relate back to the jailbreak? Well, because we have kernel memory read and write, we can inject our own code into the kernel space and call that code as the kernel and make any modifications to the system that we want, essentially. One of my favorite modifications to do once I have TFP0 is to get rid of the volume HUD, because it's terrible. Also, if Apple made a car, I bet it would look like that.
With the Garmin GPS in the middle?
Oh, of course. Yeah, no, why would they have CarPlay? That's so last year. Yeah, so that's essentially it. If you want to read the write-up, it goes into a lot more depth than I can here. I wasn't sure how long this would take, but if I had gone into any or either of the other two things that I kind of hand-waved over, this would have been a much longer talk. And then also the previous talk that this was going to be was voucher swap. And I got a little bit of information from the Project Zero about that, which is also another good read. It's a bit shorter and assumes you know a lot more than I do. And then I always like that the developer.apple.com has an archive of the really kind of older stuff. So that archive of the mock stuff is from probably around OS 10.8 when they introduced KALSR. So, yes. Any questions? I know that was a lot, and I skipped over a lot also. No? Good. Cool. Thank you.